K2-18b weighs 8.63 Earth masses and has a density of just 2.67 grams per cubic centimetre, too light to be rocky, too small to be a gas giant, and that structural impossibility is exactly why what JWST found in its atmosphere is the most contested exoplanet life sign in the history of the search. K2-18b sits in the habitable zone of a red dwarf star, wrapped in hydrogen and possibly covered by a global ocean. The James Webb Space Telescope pointed 3 of its instruments at this world and captured a spectrum that split the astrophysics community in half. One team at Cambridge says they found dimethyl sulfide, a chemical fingerprint of marine biology. Multiple independent teams say the signal is noise. What follows is every piece of evidence, every counter-argument, and what it all means for the search for life beyond Earth. In 2023, Niku Madhusudan and his team at the University of Cambridge pointed JWST's near-infrared instruments at K2-18b and detected methane and carbon dioxide in its hydrogen-rich atmosphere. Those detections were robust, confirmed at 5 sigma and 3 sigma respectively. But buried in the same data was something far more provocative, a faint, tentative trace of dimethyl sulfide, or DMS. On Earth, DMS is produced almost exclusively by marine phytoplankton and ocean-dwelling microbes. No known geological process generates it in significant quantities. If that signal was real, it would mean biology might be shaping the atmosphere of a world 124 light-years away. But at that point, the detection was barely above the noise floor. To strengthen the case, Madhusudan's team needed a completely different wavelength range, and JWST had one more card to play. In April 2025, the Cambridge team published new data from JWST's MIRI instrument, which observes in mid-infrared wavelengths between 5 and 12 micrometers. This is a completely different part of the electromagnetic spectrum from their original near-infrared observations. In this new spectral window, they reported features consistent with DMS and a related molecule, dimethyl disulfide, or DMDS, at roughly 3 sigma confidence. Madhusudan argued these mid-infrared detections constituted independent evidence, a second line of data pointing toward the same biosignature molecule. But 3 sigma is not 5 sigma. The standard threshold for a confirmed scientific discovery requires the signal to be so strong that there is less than a 1 in 3.5 million chance it occurred by random noise, and 3 sigma sits far below that line, which is exactly where the controversy ignited. To understand why K2-18b matters so much, you need to understand what kind of planet it might be. K2-18b has 8.63 times Earth's mass and 2.61 times its radius. Its density, 2.67 grams per cubic centimetre, falls between Earth and Neptune. That rules out a simple rocky world. Madhusudan proposed in 2021 that K2-18b belongs to a new class he called Hycean worlds, planets with a thick hydrogen atmosphere sitting above a global liquid water ocean. The word itself is a blend of hydrogen and ocean. If K2-18b is truly Hycean, then the conditions beneath its atmosphere could be surprisingly hospitable: warm water, organic chemistry, and energy from its star. That is the scenario in which DMS makes sense as a biosignature. But not everyone agrees that K2-18b even has an ocean, and alternative explanations could unravel the entire hypothesis. Within weeks of the April 2025 paper, multiple independent teams challenged the DMS detection. Jake Taylor reanalyzed the same MIRI data and found that in 5 out of 6 statistical tests, the data preferred a flat, featureless line over a model with spectral features. His conclusion, the claimed 3.4 sigma detection, was not statistically robust. Luque and collaborators at the University of Chicago went further. They combined all available JWST data, near-infrared from NIRIS and NIRISPEC plus mid-infrared from MIRI, into a single joint analysis spanning 0.7 to 12 micrometers. Their result, insufficient evidence for DMS or DMDS. They found that several other sulfur-bearing and carbon-bearing molecules fit the data equally well. The signal attributed to DMS was not unique, it was degenerate. The same spectral bump could be caused by ethylene, chloroethane, or other common photochemistry products with no connection to life whatsoever. Then came one of the most ambitious analyses in the entire debate. Wellbanks and colleagues took an agnostic approach. Instead of testing for DMS specifically, they ran atmospheric retrievals against a library of 661 different molecules. No assumptions about what should or should not be present, just pure statistical pattern matching across the full spectrum. Their finding was devastating for the biosignature claim. The current data do not robustly constrain any individual trace molecule. DMS was one of many candidates that showed weak, ambiguous signals, but none reached the level needed for a confident detection. The data were consistent with dozens of non-biogenic molecules. K2-18b and Madhusudan later published their own broad search across 650 molecules and found DMS was the only candidate that consistently met their minimum Bayes factor threshold, but even they stopped short of claiming a confirmed biosignature. One of the most striking findings came from the Stevenson team's assessment, when they tested different ways of binning the MIRI data, grouping the raw spectral measurements into wavelength bins of varying widths. Only 12.5% of binning configurations produced support for DMS or DMDS. The other 87.5% showed no biosignature signal at all. This matters because the way you slice your data should not determine whether a molecule exists. A real, robust signal would survive regardless of how you bin the spectrum. The fact that it appeared only in one specific binning scheme suggests the feature may be an artifact of data processing rather than a genuine atmospheric absorption line. Stevenson's team concluded plainly, K2-18b does not meet the standards of evidence for life. That phrase became a lightning rod in the community, but the statistical argument behind it was difficult to dismiss. In July 2025, NASA organized what amounted to a scientific stress test. Ren Hu at the Jet Propulsion Laboratory led a Bayesian multi-team reanalysis, combining 4 new JWST transit observations of K2-18b with the original data. 3 independent teams each developed their own interpretation using a range of possible atmospheric compositions rather than a single model. By comparing results across these teams, they could identify which conclusions survived regardless of modeling choices. The result was nuanced. Water was confirmed robustly, with the atmosphere potentially comprising as much as half the planet's mass. Methane and carbon dioxide held up. But when it came to DMS, the new analysis found a tentative signal at roughly 2.7 sigma, slightly below even the Cambridge team's earlier 3 sigma claim. The word from NASA was careful, promising, inconclusive, and in need of more data. The entire DMS argument rests on K2-18b being a Hycean world with an ocean. But several competing models say it might not have an ocean at all. Wogan and colleagues argued in 2024 that the observed methane and carbon dioxide abundances are consistent with an oxygen-poor sub-Neptune, a gas-rich atmosphere with no liquid water surface and no need for biology to explain the chemistry. Shortall proposed yet another possibility, a gas dwarf with a surface magma ocean underneath, a scenario that produces broadly similar spectral signatures. Sinai and colleagues modeled the photochemistry and showed K2-18b's composition could arise from purely abiotic processes. If any of these alternatives is correct, then even if DMS were definitively detected, it might not require life to produce it. The planet's identity is as uncertain as the molecule everyone is arguing about. Despite every rebuttal, DMS has not been ruled out. Even Madhusudan himself has been precise about this, stating publicly that his team found evidence at or below 3 sigma, which he characterizes as moderate evidence or hints, not a strong detection. The 2026 K2-18b study, scanning 650 molecules, found DMS was the only candidate that consistently passed its minimum screening threshold across both mid-infrared and near-infrared datasets independently. That is a narrow result, but it is a real one. No other molecule in the library matched that pattern. The honest scientific position, the one that most researchers now occupy, is that DMS remains a plausible candidate, not confirmed, not disproven. The spectral features are there, faint and ambiguous, sitting right at the edge of what current instruments can resolve. The question is whether more telescope time can push that edge. K2-18b is not alone. In 2026, Madhusudan's team published the mid-infrared transmission spectrum of TOI 270D, another temperate sub-Neptune observed with JWST's MIRI instrument. The two spectra look remarkably similar. After applying a small offset, most data points are statistically consistent, and the similarity was quantified with a p-value of 0.09. If the features in both spectra are real, they are not random noise, because the same pattern appearing independently on two different planets around two different stars would be an extraordinary coincidence. That result motivated calls for further MIRI observations of both worlds. The K2-18b debate is no longer just about one planet. It is becoming a test case for whether JWST can detect trace molecules in any temperate sub-Neptune atmosphere, a question whose answer reshapes the next decade of exoplanet science. The path forward requires three things. First, more transit observations of K2-18b to push the signal-to-noise ratio above the 5 sigma discovery threshold. Second, laboratory measurements of DMS and DMS absorption cross-sections at the temperatures and pressures relevant to K2-18b's atmosphere, because current reaction rate data are incomplete. Third, independent confirmation using instruments beyond JWST, because a true biosignature detection demands reproducibility across telescopes. Even Wellbanks, one of the strongest critics of the DMS claim, has said this kind of evidence could be found in our lifetime, but it will be a slow build requiring consensus among astronomers, physicists, biologists, and chemists. K2-18b has not proven that alien life exists. It has proven that we now have the tools to ask the question seriously for the first time in human history. K2-18b gave us the most tantalizing hint of biology beyond Earth, and then dared us to prove it. But while that debate unfolds, another mystery has been waiting since 2017. A cigar-shaped object that tumbled through our solar system, accelerated without any visible tail, and vanished before we could catch it.